So, my name is Emil Lindfors, and I'm here to talk a little about the art side of computer graphics, and in this context, real-time computer graphics. Because all weekend we've been seeing code and cubes and all kinds of other awesome demo scene things. But if we take a look at modern games or stuff like that, well, it's obviously not just cubes. So I'll try to shed some light on the process, like what do the CG artists do so that to get to the final product. And well, real-time asset pipeline, that would be real-time games and demos, assets, 3D models and animation and textures and pipeline. Well, how it all gets done. So you can find my slides over there. Feel free to skip ahead, but still listen to what I'm saying. So first of all, I'll be giving an overview, but this presentation will be way more fun if you can actually take something out of it that you can still use before the demo compo deadline. So I'll be showing a little sculpting thing and some code as well. And a word about myself. I'm a student here in Aalto. When I started uni, I really did not have any clue about CG art or how it's made, and then I got into demo scene and computer graphics programming, and through that I got interested in the content creation process. So basically I got frustrated at how slow it is to make beautiful images using just code. So I read up on the tools. And here's some stuff that I've done. So these are basically, you can see the triangle counts on these little wireframe images of these assets. Basically stuff that's meant to be used well enough. If this was something that's for a modern game or similar, there would, there could be hundreds of things like this on the screen at the same time. Computers and code have gotten so powerful. And here's another really little thingy that was done in Unreal Engine. But that's enough of me. So what I'll be like, here's an overview of the art pipeline. Basically, all this could be done by a single person, but mostly is handled by separate people. For example, in a game studio, there are artists who create concept art, and then the orange part, which is the modeling and texturing process, that would be handled by a single person or multiple people in a larger thingy. And then there's rigging and animation that I won't be talking about today, but is also something that takes manpower and skills. And then there's, well, game logic rendering. Things that somebody has to figure out, which is most likely or usually not me. And I'll just start explaining how the whole thing works. So a high poly model. So basically today we'll be talking about this guy. So this is a model that I made for demonstration purposes for this presentation. It's a character. If somebody comes up with a name for him, feel free to shout it out.
Jarmo.
Excellent. We have Jarmo here on the screen. And I'll be basically explaining how Jarmo got here. So, first off, I'll be outlining the process behind Jarmo, but this is only one way to do things. There's There's lots of variations for characters and other stuff. That could be, things could be done differently as well. So, first of all, I wanted to create a high poly model, which is, as you can see on the slides, basically first you create the full vision of the object or character that you're trying to create using, and you do not worry about what the game engine or the final environment it's gonna be in. You don't worry about the limitations. You just use a software that can, well, in this case, that can work with millions of polygons. And here's another explanation of the workflow, and I'll show how it happens. So, in this case, I created a base mesh using a program called ZBrush, and its feature called Dynamesh to create the basic shape of the model. So here's Jarmo in his full untextured high poly glory. This is 2,300,000 polygons. And how I got here, well, I first off started creating a base mesh, and that was done. I'll just start a new thingy here to show you how it was done. So basically with ZBrush I can take a sphere here, I can enable Dynamesh, and I can enable symmetry, and I can also let one of our audience members answer a question.
Sure.
I mean, ask a question. Go on. If the mic works. Well, just ask.
Dynamesh do?
Dynamesh? Yeah, I'll get to it. I'll show it first, and then I'll explain, and then, well, we can have a speculation about the math behind it or not. So here I can symmetrically sculpt on this thingy. So basically, if we had Jarmo there, I was creating his facial features, for example, like this. Let's see, I try to create a mouth here, but due to being slightly nervous, I do not get a very good result, but you'll see how it works anyway. So, so with basically the geometry that I have here looks like this. These are the polygons that I'm sculpting right now, and if I wanted to create a very much different shape than what I have here right now, I could start pulling on the geometry like this, and as you can see, the polygons become stretched, and that's not good. That's going to cause problems if I try to create some little details over here. For example, we have weirdly shaped polygons, so I just end up with weird and bad looking stuff. So I use Dynamesh with a magic gesture here. We wait for a moment, and it's basically created a voxel grid and just recreated the shape using evenly sized polygons, so I can keep on sculpting awesome little stuff here. So basically I did what I just showed for a while, and we ended up with Mr. Jarmo, who hangs out here right now. And this was the base mesh version of him. Then, when we have a base mesh, let me just duplicate it so that we can keep on working here. So now we are at 35,000 polygons, 35, yeah. And I have like the basic shape, main shapes outlined, but now I want to create some more details. Stuff like, well, if this was a realistic human character, for example, I'd be thinking about adding skin wrinkles or skin pores, like little tiny stuff that's here. For this demo, I've just created something simpler, just these patterns on top of his skin. And so at this point, I have a base mesh, and to have enough resolution to actually create the little wrinkles, because if I'll divide what I had here previously like this, so I can work on this nice smooth surface, because as an artist it's more fun to just not think about how the polygons go and just go on painting like this. And yeah, I guess at this point it would be nice to say that I'm working with a Wacom tablet. This is just a basic one. There are fancier ones out there, but if you're sculpting or working with graphics, it's usually fun to work with a pen rather than a mouse. And yeah, so the next step that I went through, I subdivided the model. As you can see now, Jarmo 2 is at more than 2 million polygons, and I can create some really nice tiny detail. And I did that for a while, and here's the final Jarmo, or the final geometry of Jarmo. And yeah, so that's basically the process in this case of creating a high poly model. It could be something completely different if you're making say a weapon or some other, like a vehicle or some hard surface thing you'd be modeling and clicking on in Maya or 3ds Max or something. A question?
Yeah, I think at this point it would be nice to tell them what platforms is this available for and how much does it cost?
Yeah, sure. So ZBrush is Windows and OS X, costs 700 euros or so. Basically, it's what they use for high-end game and film production, like you've seen Pirates of the Caribbean or similar, like David Jones was done using this piece of software. But if you want to get started with sculpting, there are free alternatives, for example, which will definitely get you started and get you far. Also, yeah, there's this software called Sculptris, for example, which is by Pixelogic, the makers of the ZBrush, and it is nice for starting out. And I actually have a software slide later on in the presentation, so I'll just keep moving on for now. So this was this phase. Then the next step is creating something engine ready. So if we'd have 2 million polygons. Well, these days there are computers that can work with 2 million polygons in real time in some cases, but generally you don't want that, especially as the same amount of detail can be captured in a way more efficient way. So next we'll retopologize the model and create a low polygon version of it. And I'll show you the final result and then a little hint of how it's done. So basically, what I have open here is Maya, a general purpose 3D graphics application used for modeling and animation and rendering and other stuff. So here's Mr. High Poly Jarmo. I actually just clicked on him, and as you can see, it took a while to even select the model because there's so many polygons, and we are seeing the wireframe version of him, which looked from afar is just green because there are so many polygons. But if I zoom in, you can see that there's actually a lot of detail here. Yeah, and that's too heavy, although Maya can handle him in real time. But we want to create something resembling this, which is much lighter. And also with a model like this, we can way better control how the model deforms. For example, if we were to animate him, like change the position of his hand. This is ugly, but anyways, if we did it if we manually optimize, create a nice topology for the model, we can make sure that there's no weird artifacts when we start animating. So how I did this was, I'll just create another mesh again. It shall be a cube, we will not use it. So I took Jarmo. There's multiple softwares to do the same thing I'm doing here, but in Maya this is how it works. I'll start using this feature called Quad Draw, and place some points here. Create a polygon here. So basically this is the first one of the polygons we saw on the other models. Other model, and then I can start, for example, extending the edges here, so I can basically draw a shape on top of another using fancy, well, there's some fancy projection mathematics going on behind the scenes, which I'm not very well versed in myself, but they're there and we can work nicely like that. So as you can see, here's the little patch of geometry I just created, the start of the new model, and I did this for a while and ended up with a nice light and pretty well functioning version of Mr. Jarmo. And yep. So returning to my slides, we were basically here. What I was doing was retopologizing by hand. You could also just avoid the retopol, like doing this by hand, which, for example, in this case took me, well, more than 2 hours, let's just say. And there's this push button solution called Seam Remesher, which sometimes produces nice results, sometimes it doesn't. For example, if I take Mr. Haipolu Jarmo and Z-remesh it with a target polygon count of 2,400, I'll press a magic button, wait for a while. There's a progress slider up there on the left. And my slow laptop processor, or it's not that slow for a laptop, but it's a laptop still, will give us something resembling what I just showed, a low poly mesh, but often it's not suitable for use right away. There might be weird spirals and stuff. So here you see it. It's actually pretty close, pretty similar to what I showed you before, which was done by hand by me. But well, it depends on the case. Sometimes it's better to save time. Sometimes it's better to do it by hand. And I'll just return to my last slide for a quick moment. So this line here, we need to define the silhouette of the object or character. Basically, if we look at this model from the side, there's these huge gaps and stuff like this. All this we want to model in geometry. But little details like well, the skin surface here, which is represented by, well, basically dots in space here, vertices. We actually want to just create some geometry that's close enough, or just like resembles the major shapes, but all these little details we can use textures for, which is what I'll get to next. So we don't want to be creating tiny polygons here that would model each of these little crevices. That would be a waste of time, and the model would be too heavy still after that process. So Before I explain the textures, or before the textures, there's this step of UV unwrapping. So, as you can see on the first line, we need to match a 3D shape to a 2D plane so that we can use just basic image files to define the surface of the model. And that's another thing I'll quickly demonstrate here. I had the UV editor here. Where's my model? Here. So here's the low poly Jarmo. Here is what his UVs look like. I hope you can see the wireframe grid here. It's not the clearest thing on earth, but basically what I've done here is start out with a mess, which was before this UV layout. There were just a bunch of polygons here laid on top of each other and just in weird positions, so that if we were to map a texture here, it would just basically look horrible and be all useless. But I used a tool called Auto Unwrap UVs in Maya. Which works something like this. So this thingy lets me define borders, or I mean UV seams. So basically I'll be selecting edges where I want the texture to be split, because, well, an object like this you cannot just, or like a waterproof mesh, you cannot just lay it flat on a texture. At some point it will overlap, so you'll have to cut it so that it looks correct. So I'll just select a few of these edges to demonstrate you what I mean. Add borders. So right now those edges are defined as seams, and now as I press continue, Maya does some automatic magic and we end up with this. So this is the, basically every face that we see here has been mapped to a texture, I mean to some place in the 2D texture that we're seeing. To make it clearer, I'll just show you here. So basically these faces live at this point in the image file. In a 2D image file, I'll be creating a map of the colors and other information, for example, normal information in an image file. And what I've done here is how the computers and the rendering pipeline knows which pixel on a 2D texture goes where on a 3D model. So I hope I made that clear. If not, you can come ask me after the presentation. And then we get to texture baking, which is, well, there are a few purposes for baking textures, but I would say the most common is to create a normal map from a high poly model to a low poly model. In this context of games and real-time graphics, this would be the most common reason to create a normal map. So a normal map, or the normal map for this guy, looks like this. I hope you can see it. Here it is in full screen. So I hope you guys are familiar with normal maps. If not, I'll explain really quickly. It's just, these are just vectors stored in the RGB channels of an image. So basically, this is just saying that a specific point in the image, which is, as we just saw, is mapped to the 3D model, the surface would be pointing here, for example, or some direction. So that's how we sort of fake the appearance of 3D. I mean, actually, I'll explain the whole thing. So we fake the appearance of the little crevices and little details by in our lighting calculations saying that light that hits here, for example, is treated as if it's coming from a certain direction, and right beside it there's another pixel on the texture that tells that the engine that the light, that the surface of the object is facing, for example, this direction, and then we should treat the light accordingly and shade the whole thing accordingly. I hope you got something out of that explanation. But yeah, so I used, in this case, I used this tool called XNormal to create those maps. And it's basically from an artist perspective, it's basically a tool that takes in a high poly object file. This highpoly.obj is what I've exported straight out of ZBrush here. Here, export button magic, yay. And then takes as another input a low poly object that is for some reason called cage in this case, and also it can use a third input called, well, which is the cage, to guide the projection, because all this happens by the whole texture projection thing happens by taking rays from the low poly model as it is overlaid on top of the high poly model. I'll show you. I'll just hide this guy because he's not what's used for the baking, because he's in a different spot. So we have basically, for all the math heads out there, basically we have a low poly model and a high poly model overlaid on top of each other, and we shoot rays from a surface, well, towards its normal or towards what's defined by a cage mesh, and see where the rays hit the high poly model, and based on that we create a texture to store that info and use it later. So that's that. Other types, there are other types of baked textures, texture maps as well. An ambient occlusion map looks like this, and it's used to create fake shading basically. So this map here tells that, well, it tells that, for example, here in the mouth of the character there is likely to be an enclosed space which has been inferred by looking at the shape of the object, and there's likely to be shadow in there. So it's a way of faking shadows. And I also have generated a cavity map here, which tells where there are little, well, cavities, as it says on the model. This can be useful for masking, for example, if you're painting a texture and you want some color to appear only in the cavities. For example, you could tell a painting software that, well, based on a cavity mask, when I paint here, if there is a cavity, apply paint. If not, do not apply paint. And then there's a curvature map which defines the roundness of the object, which can also be useful when generating textures. And what else I have here? I have a material ID listed here, which is a material ID map. I don't have an example here, but it's just a simple map that would define that one thing for example, if I had a material map here that said that that had green parts, or everything that we see in green here would be in one material, and everything else apart from the eyes would be in another material, and the eyes would be on a third material. I would have a material map with 3 different colors, and again, I could use that as a mask for either as an artist, as a mask for what I'm painting, or at the final rendering process, I could use it as a mask for choosing which shader and with which masks, which shader to use, and with which textures to draw that surface. So that's that useful sometimes. Then texturing. So we at this point we've generated a low poly model and some textures, like baked textures for it. I'll actually try to show what it would look like here if I disable this layer. Yep, we can see the whole thing here in this software called Substance Painter. So this is the low poly model, as you can tell by how pointy the edges are. It's not a nice high poly model. It's a low poly thing meant to use. I mean, nowadays this would be for a mobile game. Something this low poly. So we have that, and then we have the normal map texture, and with those two things, we've somewhat closely replicated the look of the original high poly model, the 2 million poly model, using only, in this case, 2,500-ish polygons. And I'll disable the normal map for a second so you can see the effect of that. So here, this is the low poly model shaded and with but without a normal map, and actually there's some traces of another map showing here somewhere. Yes, I've got the Ambient Occlusion Map on still. I'll disable that and the curvature map as well. So yeah, this is just the low poly model, and now when we enable the normal map, it shows us all the little details. But I chose the wrong map, but here. Oh, wait, no. Awesome, this is the normal map. Yeah. So as you can see, the little details that I've sculpted in there are there visible, but it's actually a flat surface that's only lit according to the normal map. And I'll just rotate the light around to show you how it behaves when lit from different places, like this. And what I'm using for the lighting here is a environment map. So basically this image here of a nice outdoor day is what's driving the calculations behind the lighting of the model. And that's what I was rotating around to see the effect of the light moving. And yeah, so that's that. And now we get to the actual final texturing and defining the colors and behavior of the surface. As said here, it can be done in either 2D or 3D. It's just the textures are just normal image files, so any way you can get to a nice final result is fine. Before all the fancy 3D painting apps, people apparently did that using Photoshop. I'm a newbie, so I went straight to the nice stuff. But this could be just painting or photo editing inside Photoshop on top of the UV wireframe, which was this. So I could just open this as a layer in Photoshop and start painting on it, and I'd later see what the result looks like when I import it into a game engine. But nowadays you can also 3D polypaint or 3D paint, and the difference here, 3D polypaint on high poly means that I would be painting on this model here, the 2 million polygon model, or higher, like in a high-end thingy, it would be like 20 million or something. So I'll just show you what that would look like. I'll just select the color. So I could paint on this, and right now as I'm doing this, the color info is not stored to a texture, but it's stored to the vertices of this surface. So all these millions of vertices, or the ones that my brush is affecting, are updating. There's not yet any connection basically between this and a 2D texture. So this is another thing that could be baked into a texture map using a baking software. Just the same projection stuff, ray casting and looking at hits. Or if we're talking about film, animation, VFX, the whole baking thing could in some cases just be skipped altogether and use so-called PTeX textures for texturing. But that's another matter. So that was 3D poly painting. We can also 3D paint directly on the low poly model that has been treated in all these little all these ways. So that's what I've done in this case. And here we have Mr. Jarmo again. And I'll show you how that works. So maybe this demonstrates the texture better than the earlier shown wireframe from Maya. So in this app, it works basically like, or there's a lot of similarity with Photoshop, but there's the whole 3D thing included in a really nice way. I'll just choose a material here. Say I'd want to give Jarmo some gold teeth. I would choose gold as my material. And as I start painting here on the teeth, you could see the material or the texture updating if we had zoomed in close enough. So if I undo a little bit here, basically I'm painting on the 3D model and it's updating the whole thing at the same time. And as you can see, the projection went a little funny, or I've done some funny stuff so the mouth has green in it, but anyways. I could also be painting directly on the texture if that happens to be more convenient. And the result would be updated directly through to the 3D viewport. And as you can see, I'm painting with gold. So I'm not just painting the color yellow, but I'm also painting the reflective properties of the material. So if I again rotate the environment that we had visible here, you can see that it reflects really nicely and behaves differently than the rest of the model. This is, well, the whole concept behind this is physically based rendering, which is very popular in real time or games, the next gen games. Read up on it. And if you're an artist, you'll very likely come across it. And I'll just show you the different channels that like. The magic of this program is that I'm painting basically 4 things at the same time. The color of the material, height, which means basically height from the surface of the model, so I can actually modify basically the normal map directly. Then roughness and metallic of the material. So I'll show you the actual layers. Here's the base color. So this is the color without any shading applied, with no contribution at all from the environment, no contribution at all from any lighting calculations. Then There's the height map, which, well, what we're seeing here is just only what I've painted using the gold, because when I was painting the model in the other phases, I had my brush had no height enabled. But if I wanted to, for example, create let's see, some crevices here, like it was a Jorma the shark, for example. He had little breathing holes here. I could disable a bunch of stuff here. That would be using these little buttons. Now I'm only working on the height layer, and as you can see, as I paint, it's basically creating the same kind of surface structure as the normal map texture that's applied underneath. So there's no color in for it or anything, but when we light the model, it behaves like the light, like these parts that I just painted in would be higher. I did not create the shark-like breathing holes, but whatever. And so it reflects light just like there was something there. So that's that. So that's the height layer. And as you can see on a texture map, in 3D it looks like this, and on a texture map, on the original 2D texture map that we have here, it looks like this. So again, this is just a basic image used as an input for lighting calculations. Then there's the roughness map. Apparently the gold and the eye material that I've used is very glossy, non-rough. So that shows as a dark value on the roughness texture. And again, that affects how the computer treats the surface when it's been shaded. And then there's metallicity. This is pretty random right now, but if we had an object, or I mean if Jorma was holding a gun, for example, the gun would show in white. We would want to define the metallicity as 1, which is the color white, obviously, in a texture, so that the engine knows that this is metal and shades it accordingly. So these are the 4 layers in this case that I used to get to this end result. And obviously these are just image files, so there are multiple ways to get here. I could just polypaint the whole thing, all 4 layers separately, and end up with the same thing, but this software just happens to make it really convenient and intuitive to edit them all at the same time. And well, PBR is not the only shading model, obviously. It's popular right now, but and it's nice because it's based on physics to quite to a large extent. So. And now today's computers and consoles can handle it. So it's nice, but that's not the only way to do things. Then, well, I've mentioned procedural textures here. Not all textures are painted or done using photos. I actually did not show anything about photos here, but I could also just be using some kind of photo projection here. So I would paint here, and it would take a photo as an input to define the surface that I'm painting on, which is also very nice in a lot of cases. But procedural textures, I could also be using some sort of a code created texture or some sort of a node graph based texture generator or some pre-made node procedural materials and applying those to my mesh. But well, in this case, I did not do it, and I won't be going too deep into that in this presentation. So that's that. I hope you have some sort of an understanding of what I went through to create this guy. And although this character is just a random cartoony looking little low poly mobile character. Most of this stuff applies from, well, in a lot of places in all the nice Assassin's Creed and The Order and similar high-end games as well, but it's done on a completely different level. And yeah, so the next 2 slides are just a bunch of resources, links, and names for you to check out later if you're interested in this stuff, to give you a nice place to start. I'll just close over them here, but well, you can see the URL here, lindfors.net/graphathon-slides, and you can spend time researching all this later. And now I'll show something that's more relevant to this weekend. So, sculpting and processing, using the sculpting processing. And where's my browser? So here, basically this thing called SculptGL, you can get to it, for example, by typing SculptGL in Google and selecting the first link, is something very similar to ZBrush, but in the browser, and well, not as featured of course, but very useful still. So here, I'm using my tablet right now. It's nice to sculpt on that, but I've done this using a mouse as well, and it's not impossible. I'll create some little thingy just for fun to show you how it's done. So there's a bunch of different tools: brush, inflate, twist, smooth, yada yada. You can start out with the drag and smooth and brush, for example. So they have the shortcuts outlined here. If I press the number 8, I'll be selecting drag. So I'll start off with that. And with drag, I can just pull out something like a longish face-like shape, and then I can press X in this program. The shortcut X lets you change the brush radius. So right now I'll change to brush number 1, which is the basic brush, and create some eye holes here. And what I did, actually, if I choose the brush and just sculpt, I get something that's protruding from the surface. But if I press Alt at the same time, Alt basically controls the direction of the sculpt. So here we have this awesome almost skull thingy. I'll just create a nose and some teeth or something. And we are done in the browser. And actually before we are done, I'll just show that this also has the Dynamesh, the magic of voxel-based remeshing. I could, if I was creating some wilder shape, like a character like this that has hands and a body and everything, and all my polygons would be getting all messed up, I could press this magic button under the topology menu to remesh the whole thing to get it workable again, but I'm not going to use that right now. So I have a mesh. This is something you could use this weekend as well, create something here. Then how to get it into processing. There's file, import, export. If I say save OBJ, magically I've just downloaded a mesh called your mesh OBJ. And I'll just move this where my processing lives. There's this folder called Monsu is just a processing sketch, as you by now are probably familiar with. There's the processing file and there's data for it. So I'll put my yourmesh.obj, which I shall rename school obj, I shall put it here in the data. And first I'll show Monzo OBJ and how to work with that in processing. So here's some processing code. Can everybody see it? Most likely yes. And this is simple. A setup function, enable the 3D drawing inside processing, use the function load shape to load a 3D mesh OBJ file, and if you do not supply any path, it assumes that it's living under the processing sketch in a folder named data, as it is. Never mind the MTL file for now, it doesn't serve any purpose here. And well, I've predefined a P-shape object called oubs to load that mesh in, and then in my drawing function I'm selecting a color for my, I'll just run this first and explain at the same time. Yes, security, awesome. So yeah, this is what we end up with. Monzo is just Jorma from earlier. And so the code, background color. Processing has a nice function called lights, which gives you an ambient light and a directional light, so that you don't have to, if you just want to see your model, you don't have to worry about where to place your lights and their colors and all that. And obviously processing is also doing all the heavy lifting and the mathematics behind lighting calculations, but that's another story. So background, lights, and then this is just basic translation and scaling and rotation to get my model from being tiny in the top left corner to rotating on the center of the screen, and then a function called shape, and it draws the shape that we loaded in load shape. This is the load shape, and shape can also be used with 2D vector graphics, SVG format files, but well, I'm more interested in 3D. So this is the example code that I used. It's almost a copy paste from processing examples or processing reference under the function load shape. It's almost this. Tiny changes, and I'll just show you what kind of an effect it has if we define lights manually instead of using the processing given lights function. So an ambient light, I'm defining that there's some light everywhere in the scene that's of a specific color. This is something purplish, if I recall correctly. And then there's a point light that's supposed to live somewhere in front of the Monzo and have this kind of a color. So color, and position of a point light. And it looks like this. Same thing, different color, slightly different lighting. And then, what was I going to show? Oh yeah, the mesh that we just sculpted in the browser. So school.obj. I just changed back to the basic lights and change the file name here. And this should work. Should be quite a bit slower to load than the previous one, as Monzo is only 331 kilobytes, but the browser sculpted one is quite a bit bigger. Well, there was no manual fancy retopology going on. It was just sculpting and straight output. So press run. Wait a moment. This might be very misplaced, as my translations are the same as on the previous models, but yeah. But, well, we are inside the school right now. So, as you can see, it's easy to get that running. I guess I'll translate it a different amount. For example, put it deeper. Just the what?
Scale less.
Yeah, I'll be also scaling it less. Something like this, maybe this works better. Just to get some fancy, nice looking output for the end of my presentation. No, not much nicer. Anyways, you get the point of the whole thing. You can figure out this basic 2D mathematics on your own. So that's that. My example code is on this slide. My 3D model, the untextured version, is also available. Lindfors.net graphathon-monsu. And that's all. Any questions?
What about texturing and processing?
Texturing and processing. You'll have to figure it out, but basically it's easy to create. It's easy to create like single shaded, single color models, of course, and apparently importing textures is also pretty easy. Or if you have vertex colors in your OBJ files, is that even possible? That should be easy, but yeah.
Well, it's possible, but I don't know if it works with
Yeah, exactly. But I just did not have time to research it for this presentation. Should not be impossible. Other questions? So, I guess I was somewhat exhaustive as there are no further questions, but come say hi and ask me about this kind of stuff. And I would love to see some demos tomorrow that use something sculpted in 3D, if you can make it. That's all.